Good evening, sir. Today in this presentation I am going to explain about impedance matching concepts in RFID transponder design. So before going into the topic, let me introduce myself. My name is Bay Saichan and my roll call is 21951A1269 and I am from IT department B section, Institute of Aeronautical Engineering, and the subject is Basic Electrical Engineering. So in this presentation, we analyze the impedance matching concepts in passive radio frequency identification transponders, which are powered by the incoming RF energy and consist of an antenna and an integrated circuitry chip, both with complex impedances. The impedance match between the chip and the antenna can be categorized by the power transmission coefficient. So we analyze the behavior of the power transmission coefficient and the effect it has on the tag performance. So let's go to introduction. RFID is a rapidly developing automatic identification technology. Although the basic principles of passive RFID technology were developed soon after World War II, it took nearly half a century before RFID technology advanced to today's level. A typical backscattered RFID transponder consists of an antenna, an integrated circuit which is called as chip. The chip is usually placed right at the terminal of the tag antenna, and both chip and antenna have complex input impedance. The system operates in the following way. Base station module RFID reader transmits an RF signal which is received by an RFID tag antenna. The voltage developed on antenna terminals power up the chip, which sends the information back by varying its input impedance and thus modulating the backscattered signal. Proper impedance match between the antenna and the chip is of paramount importance in RFID. So it greatly determines important RFID tag characteristics such as tag rate range. Impedance match can be characterized by the power transmission coefficient, whose behavior determines tag performance and can be analyzed as shown below. A specific RFID tag design example with modeling a simulation result which agree with measuring data is also presented as an illustration of the analysis. So second point, impedance matching. Consider an equivalent lumped circuit of RFID tag shown where ZC is equal to RC plus IXC in the complex chip impedance and ZA is equal to RAXA is the complex antenna impedance. The voltage source represents an open circuit RF voltage developed on a terminal of a receiving antenna. The chip impedance includes effects of chip package characteristics. Both ZA and ZC are frequency dependent. In addition, chip impedance ZC may vary with the power absorbed by the chip. The antenna is usually matched to the chip at the minimum threshold power level necessary for the chip to respond. So this is the diagram, RFID transponder equivalent circuit. So the amount of PC that can be absorbed by chip from the antenna is given by PC is equal to PA into T, where PA is maximum available power for the antenna and T is the transmission coefficient. PA is the power that can be dissipated at the chip when ZC is equal to Z into A. The power transmission coefficient T is given by 4 RPRC by ZC plus ZO square and can be plotted directly in complex impedance plane as shown below. The power transmission coefficient T directly characterizes the degree of impedance match that between the chip and antenna. Normalization equation 2 by R2 allows one to obtain. So this is the formula. So where Ra is equal to Ra by Rg is normalized antenna resistance. Xa is equal to Xa by Xc is normalized antenna resistance. And Q is equal to Xc by Rc is the response factor of the chip for the given frequency and absorbed power. Antenna impedance can be normalized to chip impedance because an RFID tag antenna is usually matched to given RFID chip. After several straightforward mathematical transformation, equation 3 can be expressed as RA minus 2 by R minus 1 bracket close whole square plus Q square bracket XA plus 1 bracket close whole square, which is equal to 4 by t square into 1 minus r. So one can see that equation 4 describes an ellipse with the aspect ratio q and center located at a point. Figure 2 shows the contour of constant t given by equation 4 for two different values of q. So this is the contour of constant power transmission coefficient T on normalized antenna impedance planes. So since ZA and ZC are both frequency dependent, both aspect ratio and foci of ellipse are also frequency dependent. At a given frequency and power into the chip, any antenna impedance ZA corresponds to an unique point RAXA and hence to particular value of T determined by the ellipse passing through the point. The contour shows in figure 2 are good illustration for the impedance matching in RFID transponders. The smaller is the ellipse, the higher the value of the power transmission coefficient. The point of perfect complex conjugate impedance match between the antenna and the chip. The point of perfect complex conjugate impedance match between the antenna and the chip in the point where t is equal to 1. Transponder range. One of the most important characteristics of RFID tag is its read range, and limitation on the range is maximum distance at which tag receives just enough power to turn on and scatter back. Another limitation is the maximum distance at which reader can detect this scatter signal. The read range is smaller of the two distance. Typically, reader sensitivity is high enough, so read range is determined by the former distance. In free space propagation environment, the power received by an RFID antenna can be calculated using free space equation as PA is equal to PT GT GR into lambda by 4 pi d whole square, where PT is the power transmitted by the reader, GT is the gain of the reader antenna, GR is the gain of the receiving tag antenna, lambda is the wavelength, and D is the distance between the reader and the tag. If the minimum threshold power necessary to power up the chip is Pth, the read range R can be calculated as R is equal to lambda by 4 pi square root of Pt by Pth Gt Grt. The peak of the range in the frequency domain can be referred to as tag resonance. Typically Pt, Pth, Gt and ratio varying, and T is dominant in frequently dependence and permanently determines the tag resistance. The read range is equation 6 can be normalized to maximum possible range the tag when it's perfectly matched to the chip T is equal to 1. Such normalization allows designer to see what improvement in the read range can be obtained by better impedance matching. For example, for the tag in the figure 4, impedance matching with T is equal to 0.5 corresponding to about 70% of the maximum attainable read range. This is the graph normalized read range versus power transmitted coefficient. So design example. Consider a specific design example, the IntelliTag ID card developed by Intermec Technologies Corporation as shown in below figure. So this credit card format RFID tag was designed for security access and control applications. This tag is currently used for expected border crossing between the United States and Canada. This is that card. The transponder consists of an RFID chip connected to a folder Mender copper antenna printed on 4mm FR4 substrate. The copper trace area in 70 mm by 22 meters as shown in figure 5. So the transponder was designed to operate in 915 MHz band after being embedded into a plastic card. So in the figure, in the tag, Fairchild RFID ASIC chip was used. The chip was mounted on an antenna terminal using flip chip packing. So this is the figure RFID transponder inside Intel ID card. The input impedance of the packed chip was measured in the frequency domain with a network analyzer for different power levels. It was determined with RFID reader that minimum power needed by the chip to turn on was 9 dm and the packed chip impedance was Z is equal to 15 minus 420 ohms. This antenna was designed using electromagnetic stimulation TEL Ansoff Designer, which allowed us to calculate antenna gain and impedance and match it to the chip. The antenna was designed so that the tag resonates in the free space and about 965 MHz. This ensures that when the tag is placed inside plastic card, its resonant frequency shifts to 915 MHz band. The power transmission coefficient for this ant band in free space band given in figure 6 as functionation. It was calculus equation to impedance valve as measured as dissimulation in impedance valve for EM simulations. This is the power transmission coefficient of RFID transponder in figure in free space. So experimental results. The tag read range was measured as illustrated in the figure. The tag was placed in an anechoic chamber at a fixed distance from the linear polarized reader antenna. The tag face was normal to the antenna center line and oriented in the direction of best polarization match. The distance to the tag was 0.9 meters, was selected such that the tag would respond and locate both in far field. At each frequency, the minimum transmitter power PT required to communicate with the tag was recorded by using controller authentication on the output of RFID reader. So this is the diagram, tag range measurement setup. So since the gain of the transmitting antenna, the separation distance and the cable loss were known, the tag read range for a given EIRP was calculated from the equation. Equation is R is equal to D into under square root EIRP by PTGTL. So figure 8 presents a comparison between the theoretical and experimental measure range for a RFID transponder, and antenna gain GR and impedance ZA were calculated using Ansoff Designer, and chip impedance ZE was measured as described above. It can be seen that theoretical curves and experimental data are in good agreement. It can also be seen that the rate range in free space reaches maximum at the same frequency as in the free space the power transmission coefficient show. So when RFID transponder is placed in inside plastic card, antenna properties change and tag resonant frequency shifts from 965 MHz to 915 MHz. So here's the conclusion. In this presentation, we analyzed impedance matching concept in RFID tags in which both antenna and chip have complex impedance. So this is the diagram. So theoretical and experimental red range of two RFID transponders. So the impedance match can be characterized by the power transmission coefficient. We analyzed a behavior of the power transmission coefficient and the effect it has on tag performance. So we presented a specific RFID tag example and showed that the tag resonance is determined by the peak in the power transmission coefficient. The experimentally measured red range agreed well with the theoretical model. So that's it in this presentation. Hope this was informative. Thank you.